Hi, hello, namaste. We speak about Ehrenfest theorem, and in this video we will derive it. But first, we need to understand what it actually stands for. So, in quantum mechanics, any physical quantity is referred to or described as operator. Okay? And the measurements are obviously probabilistic in nature. Measurements are probabilistic in nature, which means that we cannot predict exact outcome, or we cannot say that there is this one single measurement, right? One single measurement, the concept like that does not exist in quantum mechanics. So we take an average of it, right? We take an average of such values, and this average value we call it as expectation value. So what does it mean? What does it mean when we say average value? It gives average results for a good amount of repetition of experiments, identical experiments. So let's say there is one experiment happening, then there is this. So many like this experiments take place, and they're all identical in nature. And that being identical, we can get an average value or expectation value. And how does Ehrenfest theorem comes in this picture is that the question we ask ourselves is that how this expectation value changes with time. How this expectation value changes with time. And to answer this, we have Ehrenfest. So what it does is that, this is what Ehrenfest answers, is that, like we said, it changes with time. So we say time evolution. We get an equation based on the time evolution of expectation value, right? Time evolution of expectation value. Now that we know why we need Ehrenfest theorem, so with this basic idea, we can start with the derivation. Expectation value is referred to as A, right? This is like average value, right? Average value of a physical observable, and it is measured over many identical experiments. Okay, so this is what I said. And for an operator A, right? Since we are dealing with expectation value of A, we need to have an operator A to the other side. So what it means is that for an operator A, the expectation value is defined as, you can say, the integral, which is from minus infinity to infinity. And we have a wave function x comma t. We have the operator as well. And we have a conjugate of the wave function. And since we are dealing with the space, right? So we put dx to indicate that this is over all the space. This is over all the space. Now, with the aim of Ehrenfest theorem, what we do is, since this is an expectation value, we take the time derivative of this expectation value, which is dou by dou t A is equals to minus infinity to infinity. Now, since we take the time derivative inside, we will do the product rule inside this overall expression, to which we get something like this. Dou psi by dou t A psi star plus dou psi star by dou t A psi plus psi star dou A by dou t psi and dx. Never forget dx. Now we take the very important equation, which is time dependent Schrödinger equation. Why? Because in that equation we can get the values of this two easily. Therefore, the time dependent Schrödinger equation is given by I h cut dou psi by dou t is equals to h psi. Now, of course, we need to, as I told you, we need to get this. So we rearrange it in this form. Dou psi by dou t is equals to 1 upon I h cut h psi. Similarly, we also need to have a conjugate to get the value of psi star, right? So we take it, the conjugate value. Since it is a conjugate, it is minus I h cut dou psi star by dou t is equals to h psi star. And again, we will rearrange it. Dou psi star by dou t is equals to minus 1 upon I h cut h psi star. We are going to put the values here, which we have just now got, inside our main equation. So it is going to be minus infinity to infinity and 1 upon I h cut h psi a psi star minus 1 upon I h cut, I'll keep it in bracket, I h cut h psi star a psi plus psi star dou a by dou t psi dx. So I just wrote it, what we just now did over here. Now there is a rule which we need to follow, that this is an Hamiltonian, right? H and yeah, so this is an Hamiltonian. So there is a rule that Hamiltonian on operators are Hermitian. What it means is that, let's say we have h psi star, right? So it is equals to psi star. Therefore, we can say that, let's say I have 1 upon I h cut psi star a psi, so which is equals to minus 1 upon I h cut psi star h a psi. What it means is that the Hermitian can be shifted from one side to the other without changing the value. So with this idea, we can do something here without changing its actual form. By that, I mean, we can write the equation as, therefore, dou by dou t of a 1 upon I h cut, I'll take I h cut outside, right? And it is of course minus infinity to infinity psi star a h minus h a psi dx plus minus infinity to infinity integration psi star dou a by dou t psi dx. How did we got this? Well, from this. So AH and HA, they form a commutator. So the commutator can be written as, let's say I have A comma B. So it is written as AB minus BA. In the same sense, we can also do this, the same thing over here. Therefore, from this, we can write dou by dou t A is equals to 1 upon I h cut A h plus dou A by dou t. Now you may ask how we got this. So for example, let's say we have this operator which has some psi star O and psi with dx. So it can be written as this, the expectation value. In the same sense, we did this in the same way over here and we wrote it like this. So this is our final form of equation as dou by dou t of A is equals to 1 upon I h cut this is also valid and this is also valid. Why? Because if our A does not explicitly depends on T, we can write this equation like this. This is also called as Paul Ehrenfest. Let's talk about what it tells us. So the Ehrenfest theorem now, like, it has an average value of some physical quantity which changes with time, right? This is what we discussed in the initial part. So even though the individual measures are uncertain, the average follows a clear rule, right? That can be controlled using the Hermitian of the system. So when we apply this to the position and momentum, right, we use this as an average motion which follows like the classical mechanics, which turns out to be very similar to the classical laws of motion for the example of position momentum. Okay, and with that, thank you so much for watching.